Hello. Welcome to the static video of the second series in the Introduction to the Easy Software System. In this section, the high point membrane will be analyzed under various static loads, and the design of the primary structure will be presented. The loads occurring in the individual structural components will be visualized, and by applying partial safety factors, the load-bearing capacity will be determined using an EuroCode 3 steel design. Building on the form-finding process from the first video, we remain in the project directory with the saved form-finding files. By switching to the Static Analysis tab, the static module can be launched via the central tile. The module opens in a separate window where all inputs and analyses are carried out. At the start, the project manager opens. Here, the project name is entered, in our case, High Point. Next, the geometry and surface files to be analyzed as the model can be selected. The form-finding data are already pre-configured and are confirmed by clicking the Create button. The model is then generated and displayed in the graphical interface. For the membrane surface, an equilibrium state was determined in the form-finding process using the force density method, without any material parameters. The additional primary structure was considered with preliminary design values. For the structural analysis, all components must now be assigned materials and cross-sections. The first step is to open the material database. Under Materials, set the filter in the list element to Membranes. The membrane material TechNet Default can then be added to the Project Explorer by clicking Add to Project. Next, change the filter to Cables and add the cable material 160 in the same way. Then change the filter to Steel, select, and add the material S235. Once all required materials have been added, the necessary cross-sections can be defined. In the Material Database, open the Cross-Section tab. Set the filter in the list element to Cables. From the displayed cable cross-sections, select RedILE-OSS12. In the Properties panel, the previously added cable material is automatically assigned under Material. Click Add to Project to add this cross-section to the Project Explorer. Next, the cross-sections for the struts are defined. Set the filter to RO for a circular hollow profile. Select the cross-section 101.6 by 10.0. The material is again automatically assigned. As before, add it to the Project Explorer by clicking Add to Project. Additionally, select and add the cross-section 114.3 by 10.0. The material database can then be closed. The materials and cross-sections are now assigned to the individual components of the high point membrane. First, the membrane itself is selected. By clicking the thick central point, the Properties panel opens on the left. In the Cross-Section 1 list element, select TechNet Default 1000. This cross-section was automatically generated via the assigned material. For the to-direction, the corresponding cross-section is entered directly. A special feature of membranes is that the original lengths must be calculated using Calculate link attributes. Next, the appropriate cross-section is assigned to the central strut. Clicking the strut highlights it and opens the Properties panel. By default, it is set as a beam element. Change type to strut, and under cross-section, select RO114.3 x 10.0. To select specific elements efficiently, a selection filter can be used. Access it via Select in the menu bar, then choose Filter Links. The filter menu will appear on the right side of the window. This allows all remaining beam elements to be selected at once. In the Type section, uncheck all other element types so that only beam remains active. Click the Select button to highlight all elements matching the filter criteria. In the Properties panel on the left, change type to Strut, and in the Cross-Section field, select RO101.6 x 10.0 from the list. The cone at the high point is also modeled using struts to effectively carry both tensile and compressive forces. Next, the cable cross-sections are assigned. This includes the boundary cables, anchor cables, and tensioning elements. In the filter menu on the right side, within the Type of Link submenu, deactivate beam and activate cable instead. Click the Select button to highlight all corresponding elements. By zooming in on the graphical view, the selection can be visually verified at a connection element. In the Properties panel on the left, select the appropriate cross-section in the cross-section list element, in our case, Recalculate OSS 12. All components of the high-point membrane are now assigned with the appropriate materials and cross-sections. This means the basic requirements for the structural analysis are met. The next step is to create a load case. This is done via the Add Load Case button in the Quick Start toolbar. The newly created load case LC1 appears in the Properties panel and is renamed to LC1 Faux Fin. For the first calculation, it is kept unchanged as it represents the materialized form finding. The calculation is started via the Create Result button in the Quick Start toolbar. Once completed, the calculated model is displayed in red in the graphical interface. A comparison with the form-finding model in green shows no changes. The equilibrium shape remains as desired after materialization. In the next step, the self-weight load case is created. A new load case is added and renamed LC2 self-weight. In the Properties panel, under the Dead Load section, the checkbox Apply Dead Load is activated to automatically consider the self-weight of all components. The calculation is then started again via the Create Result button. Once completed, the calculated model is shown in red in the graphical interface. By clicking Analyze Result in the Quick Start toolbar, the Options panel on the right side opens. To display the membrane stresses under self-weight, the toggle button for Link Stress must be activated. The slider can be used to scale and fine-tune the color representation of the stresses. The magnitude of the stresses can be read from the legend. In this load case, the stress distribution of the high-point membrane is largely uniform. However, locally increased stresses occur in the area of the high point where they are concentrated. The deformation plot reveals a slight deviation from the equilibrium model of the form-finding process. This is primarily caused by the self-weight loads, especially those of the boundary cables. The visual display of membrane stresses is then deactivated by the toggle button. With the stress display disabled, the next load case can now be created. Using the Add Load Case button in the Quick Start toolbar, a new load case is added and renamed LC3 Snow in the Properties panel. For the Snow load case, click the Add button in the Area Load section of the Properties panel. A new entry will appear in the left-hand list with a red background and the number 1. Select this entry and click Edit to open the property window for the area load. Under General Information, set the load type to Snow. In the Parameter section, set the value to 0.5 kilonewtons per square meter. To apply the snow load to the entire membrane surface, click the Add All button in the Elements section. Once all inputs are complete, start the calculation using Create Result in the Quick Start toolbar. For better visibility, deselect the surface by clicking on an empty area of the graphical interface so that both the calculated model and the original model are displayed. Under Snow Load, a significant sag in the red result is visible in the edge area of the membrane. For the Wind load case, a new load case is first created. This is done by clicking the Add Load Case button in the Quick Start toolbar. The newly created load case appears in the Properties panel and is renamed LC4 Wind. For the creation of wind zones, Easy provides a dedicated wind tunnel module based on open foam. In this example, however, we will not address this feature. Instead, the zones will be generated manually based on the EuroCode standard. To define the wind load, click the Add button in the Area Load section of the Properties panel. A new entry with a red background and the number 1 will appear in the left-hand list. After selecting this entry, click Edit to open the Properties window for the area load. In the Elements section, select the option From Surface to apply the wind load specifically to the membrane surface. Under General Information, choose Wind from the Load Type drop-down list. In the Parameter section, set the wind velocity pressure to 0.55 kilonewtons per square meter and the CP value to -1.4. In this case, the CP value applies only to a limited section of the membrane. To correctly represent this, additional areas are removed from the selection. For this purpose, the options No Overlap for Load Zones and Show All Load Zones are activated. These settings apply globally for the entire editing session. A new surface with ID 2 is now created and subsequently edited. Under General Information, the load type is again set to wind. In the parameter section, the velocity pressure is set to 0.55 kilonewtons per square meter, and the CP value is set to -0.6 in this case. For the area selection, the Pick Polygonal option is activated. In the graphical interface, the starting point is placed by clicking above the membrane at approximately -8 meters in the x direction. The second point is placed vertically below the object. Since this area is to be subtracted from the existing load zone, the remaining region is fully outlined and closed by clicking back on the starting point. All elements within the polygon are assigned to the new surface number 2 and simultaneously removed from the original surface. Another surface with number 3 is created and then edited. Under General Information, the load type list element is again set to wind. In the parameter section, the velocity pressure is set to 0.55 kilonewtons per square meter. The CP value is set to 0.4 in this case. The surface selection process is the same as before. In the graphical interface, the starting point is placed at -2 meters in the x direction, and the second point defines the vertical alignment. Since this surface is to be subtracted from an existing load zone, the remaining area is completely enclosed and closed by clicking on the starting point. All elements within the polygon are assigned to the new surface number 3 and as well subtracted from the previous surface. Finally, another surface with number 4 is created and edited as described previously. Under Load Type, the option Wind is selected again, and the velocity pressure is set to 0.55 kilonewtons per square meter. The CP value is set to 0.6 in this case. For the surface selection, the procedure is the same as before using Pick Polygonal. In the graphical interface, the starting point is placed at +2 meters in the x direction, and the second point is placed vertically below. Since this surface is also to be subtracted from an existing load zone, the remaining area is fully enclosed and closed by clicking on the starting point. All elements within the polygon are assigned to the new surface number 4 and simultaneously subtracted from the previous surface. Once all inputs have been completed, the calculation is started via Create Result in the Quick Start toolbar. Since larger deformations and kinematic effects are expected in this load case, the calculation process takes slightly longer, but still finishes quickly, with residuals below 0.1%. For better visibility, the surface selection is removed by clicking on an empty area. In the deformation view, it is clearly visible that the membrane is heavily indented in the left-hand area due to wind pressure, while it is lifted on the right-hand side due to wind suction. In our model, the wind is coming from the left side. As always, the calculated model is displayed in red, while the original equilibrium shape from the form-finding process is shown in green. The external loads resulting from the wind action can be visualized using vectors. To do this, open the Scale Factors tab in the Options panel and activate the toggle button under External Loads. The slider can be used to adjust the vector size. This visualization clearly highlights the areas affected by wind pressure and wind suction, allowing for an immediate verification of the load distribution on the membrane. So far, only individual load cases have been considered. To simulate realistic scenarios, these are now combined into different load case combinations. This is done by clicking the Add Load Case Combination button in the Quick Start toolbar. A new combination is created, and the corresponding submenu opens in the left-hand Options panel as usual. Here, the name is changed to LCC1 Self-Snow Wind. In the Parameters submenu, the loads of the individual load cases can be specifically added and assigned the corresponding partial safety factors. First, the self-weight is activated with a factor of 1.35. The snow load, as the significant variable leading load, is applied with a factor of 1.5. The wind load, as the accompanying load, is considered with a factor of 0.9. The load case combination is then calculated via the Create Result button. The calculation of load case combinations in membrane structures generally requires more time, as asymmetric loads can result in larger deformations and complex kinematic effects. The result of the simulation is shown in red. However, a key advantage of EASY lies in its high computational stability and robust numerical approach, which consistently delivers accurate results and reliably represents an equilibrium state. Another load case combination is created and renamed LCC2 self-wind snow. The partial safety factor for self-weight remains unchanged at 1.35. In this case, however, the wind load is significant variable leading load and is applied with a factor of 1.5. The snow load is treated as an accompanying load and considered with a factor of 0.75. The load case combination is then calculated via the Create Result button. The result of the deformed geometry is displayed in red immediately after the calculation process is completed. Subsequently, the stresses of the individual components of the load case combination can be visualized and examined. This is done via the Analyze Result panel on the right-hand side, which remains active. By activating the Link Stress toggle button in the membrane section, the membrane stresses are shown in color. In this load case, increased tensile stresses occur, concentrated along the connection from the right corner point to the high point. The exact values of the maximum stresses can be read from the legend in the right-hand panel. To review the results of the first load case combination, simply select and click the corresponding calculated load case in the Quick Start toolbar list element. The deformations and stresses of this load case are then displayed immediately. The maximum stress occurs in the area of the high point, reaching peak values of more than 52 kilonewtons per meter. All forces in the primary structure and in the cables can also be displayed. For this purpose, switch to the Cable Struts Beams tab and activate the Axial Forces toggle button. As usual, the slider can be used to adjust the displayed magnitude. In the graphical view, all axial forces are now shown in color. After completing all static calculations, we now turn to a new optional feature, the EC3 Design Interface, which can be launched via the menu bar under Options. Once opened, a separate window appears, consisting of a navigation panel, an input or main area, and an evaluation interface. In the input area, the relevant parameters can be defined, such as the selection of the national annex and the type of stability check. In this example, the setting is changed to Use Reduction Factors Check, in accordance with the requirements of the EC3 standard. Next, the load cases relevant for the EC3 check are selected. This is done via the Load Cases and Combinations button in the navigation panel. In our case, the two load case combinations are considered relevant and are therefore activated. For the analysis, the relevant components must be selected. First, the links are chosen in the navigation panel and activated via the submenu All Items, using the checkbox Check. Next, the set of links are selected, if available. Finally, the cables are also included using the option Check under All Items. All input parameters are now defined, and the EC3 analysis can be started via the EC3 Check button in the evaluation interface. After the calculation process, the results are displayed directly in the main area. For the selected load cases, the safety factor and the relevant detailed information are shown. For better clarity, the global maximum safety factor is also listed and highlighted in color under Check Result Summary in the evaluation interface. In our case, 1.62 in red. By closing the menu window with OK, we return to the Static Analysis module. Here, the safety factors of the individual elements can be visualized graphically for better illustration. In the Analyze Result menu, under Scale Factors, the Design Code Ratio toggle button is activated, and the view is adjusted using the slider. For each calculated link, the largest determined safety factor is displayed in color. This includes all calculated load cases, meaning the graphical representation is global and independent of the currently displayed load case. All factors shown in red have values of 1 or greater. In our case, this applies to the main strut, where the chosen cross-section is too small. The affected component is identified as link 104. One option would be to modify the cross-section directly at this location. However, a more elegant solution is provided by the EC3 menu. In the navigation panel under cross-section, it can be adjusted. We update both values for the struts, since the bracing struts were totally oversized. The changes are as follows. Cross-section 4 is adjusted to 76.1 times 5.0 by clicking on the value. Cross-section 5 is changed to a stronger variant, 139.7 times 12.5. By changing the cross-sections in the EC3 module, the modification applies only within the design module. In the analysis, the original cross-sections remain unchanged, and the calculation of stresses and forces continues to be based on the initial values. This is also clearly visible in the display. Based on this, a quick EC3 check can be carried out to simplify the pre-selection of cross-sections. All values are now below 1 and indicate a good utilization. After the adjustment of the cross-sections in the design check, this must now be transferred to the analysis. In the navigation panel, check the cross-section checkbox. There, both values are selected while holding the Control key, and the Export to Analysis button is pressed. The dialog that appears is confirmed with Yes. As a result, the cross-sections in the analysis now match those of the design module. All previous calculation results are deleted in this process, and no deformation figure is displayed anymore. The calculations must now be repeated for all load cases and load case combinations. To do this, select the sub-menu Create Result of any load case from the Load Case menu. A new dialog window opens where the desired load cases can be selected using checkboxes. In our example, all except LC1 Fofine are activated. The calculation is started with Start. It is important to note that for combinations, all included load cases must first be calculated, otherwise an error will occur. The calculations for the individual load cases are performed in parallel and are automatically managed by the software. Only afterwards can the calculation of the load case combinations be executed. All progress and result information is displayed in the info panel at the bottom. Once the calculations are complete, the window can be closed with Close. Afterwards, the EC3 check must also be recalculated. Once opened via the menu, the calculation can be started directly. With a ratio of 0.85 and 0.87 for the two load case combinations, the utilization is now well adjusted. After closing the design module, we once again review the design code ratio in the graphical interface and observe a uniform utilization of all designed components. After all calculations have been updated, we once again review the membrane stresses via the Analyze Results option in the menu. For load case combination 1, the stresses remain concentrated in the area of the high point and have only slightly changed. Using the list element in the Quick Start toolbar, we then switch to load case combination 2. Here as well, a similar stress distribution is observed compared to the original result, remaining almost unchanged. A modification of the stress display is the cylindrical representation. This can be enabled in the options by checking 3D cylinders/spheres. The stresses do not need to be displayed individually. Additional quantities, such as normal forces, can also be visualized. For the forces in the cables, the representation can also be modified. This is done via the checkbox Alternative Presentation of Cable Axial Forces. The slider can be used as usual to adjust the display. In the view, the undeformed and the deformed geometry are superimposed. By deactivating the original model, the visualization becomes much clearer. By changing the perspective, all stresses and forces can be illustrated more effectively. The legend always shows the active display elements, with the scale corresponding to the maximum and minimum values of the forces or stresses. Up to now, the results have only been shown in color representation. In addition, it is also possible to display the numerical values. This can be enabled in the Options menu under the Labeling Legend tab, in the Labeling submenu by checking the option Label All Data. For all active membrane, cable, strut, or beam options displayed in color, the corresponding values are now also shown. The maximum values are highlighted in red, as in this case at the high point, where the maximum stress reaches 30.95 kilonewtons per meter. With this, all static analyses of this example are completed, and the data can be saved using the Save button. All calculated data and results can be stored in a fully customizable report. The editor can be accessed via the menu option and the submenu report. Since it offers a wide range of variations and customization options, detailed information will be provided in a dedicated video. With this, the work in the static analysis module is complete, and the module can now be closed. The static analysis of the high-point membrane is now complete. In the next video of the Second Steps Easy series, we will present the cutting pattern generation of the roof structure, demonstrating how easily and partly, even automatically, it can be created. Thank you very much for your attention. If you have any comments or questions regarding the procedure, please don't hesitate to post them here. We greatly appreciate your feedback.